Hi, this is the report for Lab 4. In this lab, the goal was to analyze something similar to the extreme sports video from EDX. In this case, I'm going to analyze the motion of a spring mass system oscillating, and I'm going to create a model that is similar to the real-world motion. My procedure consisted of extracting position data from the provided video and applying fundamental physics principles to create the model. My results, in brief, are that the energy principle is obeyed in the real-world model, and that my model is slightly underpredicts the real-world motion. Once again, the momentum principle is a key concept in our lab to predict motion. For this lab, F net will be the vector sum of the gravitational and spring forces, whose equations are given to the right. I also use the position update equation in the model, and I use the energy principle equation in my analysis. To model, I had to solve for initial conditions. To solve for the oscillation period, I took the average of the time of the first 3 oscillations based on the Y position data. To solve for K, I rearranged the oscillation period equation for K and plugged in my known values. I then found the relaxed length of the spring using the last equation. In my code, I inputted the momentum principle and position updates to plot the model position versus time. I also added the energy equations in the loop to get an energy versus time graph. Here's the model that I created. The yellow dot is the fixed point that the spring is attached to. The coil represents the actual spring. The red ball represents the actual position data from tracker. The blue ball represents the position of the model, and the blue trail represents the path of the model. And here is the Y position versus time graph, comparing the actual data in red to the model data in blue. As you can see, the model underpredicts the actual position as time goes on. I think this could be due to inaccurate tracking data, which will lead to values of the oscillation period, spring constant, and relaxed spring length being inaccurate compared to the actual values. For the energy graph, I set my system to be the Earth, the mass, and the spring, so that this accounts for some of the energies being potentials, which would be part of the system. The graph shows delta K in blue, delta UG in red, delta US in green, and the total delta E in orange. Since there is no energy input from the surroundings in this graph, these energies of the system must sum to 0. We can see that delta E is constant at 0, meaning that energy is neither gained nor lost in the system, and the energy principle is in fact obeyed in this scenario. I now wanted to see how my model would be changed if I calculated the oscillation period, spring constant, and relaxed spring length by using the X position data to estimate the oscillation time. I did the same calculations as I did originally with the Y data, but this time they ended up being smaller values. Here is my original model using the Y data estimates next to the model with the X data estimates. You can see that the X data model overpredicts the motion of the spring mass. This is likely due to the oscillation time, spring constant, and relaxed length being smaller than the actual values. From this, I can conclude that those actual values lie in between the estimates from my Y data and X data, but they likely lie closer to the Y data estimates, since that model seems to be more accurate. Here are the change in energy graphs from the 2 respective models. They are very similar, only differing in the values of each value of change in energies. They do both have a constant 0 delta E, meaning that both models obey the energy principle, despite using different estimated values.